Hello everyone and welcome to this abstract algebra video. So in this video we're going to be talking about what are called normal subgroups. And so a subgroup is called normal. Really it boils down to that each of its left cosets is a right coset and each of its right cosets is a left coset. So the left cosets and the right cosets coincide with each other, right? And so the formal way of saying that is that a subgroup N is normal if for any element G in the group we have that the coset Gn, the left coset Gn, is equal to the right coset Ng. And so the notation for this is this N is, it's sort of, think about it as the subgroup notation less than G but with sort of the side closed in to make a triangle. And so the important thing to note here is that if Gn is equal to Ng, what this means is that for any n in N, there exists some N1 such that if you multiply G to the left of N, you get N1G, and so this N1 is in N. And so this means that Gn is inside Ng, and there exists some N2 such that N times G is equal to G and 2. And so this is saying, so Ng is inside Gn. And so the important thing to note here is that this N and this N1, they don't have to be the same. And same thing with this N and this N2, it doesn't have to be the same. And so if you want to move G to the other side of N, you can do that, but you have to allow that you're swapping N out with some other element of the normal subgroup. Okay, so N is normal in G, so then its left cosets are equal to its right cosets. Well, then what that really boils down to is that Gn G inverse, so we call this a double coset, is going to be equal to N for all G and G. So let's give a quick proof why this is true. So if N is normal in G, and let's use our notation. Let's go back to blue though. Then let's let G be in G, and so then we have that G times N is equal to Ng, and so then let's let N be an element of N, and so we have, that means there exists an N1 and an N2 in G, an N1 and N2 in N. Let's fix that. Gn equals N1G and Ng equals Gn2. And so if G1 equals N1G, then this means that Gn G inverse is equal to N1. So Gn G inverse is inside of N, and this allows us to conclude that since N is arbitrary, that Gn G inverse is inside of N. On the other hand, using the other one, we have that N is equal to Gn2 G inverse, and so similarly this tells us that N is a subset of Gn G inverse, so Gn G inverse is equal to N. Okay, so that gives us one direction. Now going the other way, now if G and G inverse is equal to n. This way, going backwards, it's going to look pretty much the same argument. This means that for any n in n, there exists in n1 and in n2 in big N such that G and G inverse is equal to n1 and G and 2 G inverse is equal to n. And so then the first one tells us that Gn is equal to n1 G, and G1 being equal to n1 G, this tells us that Gn is inside ng. And so we have that Gn is a subset of ng. On the other hand, the other one, we have that Gn2 is equal to ng. And so since we're focused on n, this tells us that ng is a subset of Gn. And so same as before, we have double inclusion. And so we have Gn is equal to ng. Okay. And so really this tells us how, and sort of an easier way of checking what makes a normal subgroup. And so this is what's called the normal subgroup test. And so if you have K is a subgroup of G, and then if you take any K and K and any G and G, and you look at G times K times G inverse, if you are guaranteed to land back in K, then that's guaranteeing that K is a normal subgroup. And so this right here is coming from, this really here all you're showing is that G, K, G inverse is inside of K. But the other inclusion is, this is true for any G and G. The other inclusion is pretty much automatic. So if this holds true for any G and G, then that means that G inverse KG gives you an element of K. And so this means that for any K1 in K, you have that G inverse KG, K1G, is inside of K. And so then, if you then multiply this on the left and right by G and G inverse, so then you have that G inverse, K1, G times G inverse. This is going to be inside G, K, G inverse. And this right here is just, these cancel off and you have just K1. So K is inside G, K, G inverse as well. Okay. So what are some examples of normal subgroups? Well, if G is abelian, well then Gn is equal to Ng for any G and N in the group. And so all subgroups in that case are normal. Similarly, if you have the center, so remember the center commutes with every element, and so similarly as with when in the abelian case, if you take the center or any subgroup of the center, that is going to be normal in G. So another good one to remember is that any time that you have a subgroup whose index in the group is 2, so remember the index means that the number of left cosets is 2, then that subgroup has to be normal in G. And so the idea is suppose that that n has order 2, as index 2, then let's let G not be an element of n, but G is an element of G. So G is an element of G, not n. Well then, since the cosets make up a partition, we can think about G as being in a union of n and Gn, and this is a disjoint union between these two sets. And so now let's look at n times G for any n and n. Well, since G's not an n, then ng can't be an n either. So ng is not an n, and because if it was an n, then that would mean that G would have to be an n as well, and we said that that can't be true. And so if G is not an n, and it's somewhere in either n union with Gn, then that means that ng is an element of Gn. And so the right coset is a subgroup, is a subset of the left coset, and then we could run this argument similarly on the other side to get the other inclusion. And so the only thing that has to be true is that Gn is equal to Ng. Okay, and so this guarantees that any coset that is index 2 is going to be normal. Okay, so now we're going to prove a number of important theorems involving normal cosets, normal subgroups. Normal subgroups are really important, and as we will see in these. So the first one is that if G is a group and n is a normal subgroup, then we saw this G mod n before. This is talking about the set of cosets. Well, in the case that n is normal, this actually forms a group, where the group operation, the coset an times the coset bn, is going to be equal to abn, the coset ab times n. Okay, so let's give a quick proof of this. So we're trying to show that the set G mod n, so the set of cosets, is a group. By the operation, since this operation sort of is borrowed from the operation of G, looking at how this operation is defined, it's already guaranteed to be associative, because it's really this operation between these two is really taking on G's operation. And so we already get associativity and closure. So for the identity of the group, well, n, which is the identity times n, this is the identity element of G mod n. And so the thinking here is that if you have a times n times just n, well, this is going to be we can think about this as there being a secret e here, so that'd be a times e times n, which is just a times n. And similarly for right multiplication, so the coset corresponding to the normal subgroup itself, that is the identity element. And then inverses, well, the inverse is just the obvious choice. For an, choose A inverse n, and then you have an times A inverse n is equal to A inverse n, which is really equal to n. And so this all right here is kind of just playing around with the symbols based on this group operation. What's really going on here? So what am I really talking about for when I have a times n times A inverse n? Well, what's really going on here is for any n1 and n2 in n, saying that an1 times A inverse n2 is going to land me back in N. And the thinking here, using what we've seen before with normal subgroups, is that I can take the AN1, so this is because I can take AN1 and rewrite it as N3A for some N3 in N. And so then this becomes N3, A inverse N2, which is just N3, N2. And so since N3 and N2 are both elements of N, this is guaranteed to be inside of N. And so that's really deep down what I'm saying when I'm saying that these cosets are equal. I'm saying that if you take anything on the left, any element corresponding to multiplication of something in AN times multiplication by something in A minus N, you multiply those together, you're going to land back in N. Same thing, you can do this trick the opposite way. You take something in N, then you think about it as being A inverse, A times A inverse in N, and then you can flip out and rewrite it as, well, at that point it's already is, you can think about it as A times the identity times A inverse times whatever it was in N. And then that shows that it's in the other side. Okay, so this special group, this G mod N, that we get, this group of the cosets, this is called either the factor group or the quotient group. So in Joe Gallian's book, he calls it the factor group. I'm actually more familiar with it being called a quotient group. And then usually, because it gets tiresome to keep writing the cosets down all the time, often instead of saying AN, we would just shorten it down to A bar, which is just sort of, when you're working in G mod N and you start seeing A bar, then that's what you're talking about. And if you think about it, this is similar to how we started talking about Z mod NZ. And so in that case, since Z is an abelian group, NZ is a subgroup of Z. And so our arithmetic, when we're working Z mod NZ, what we're really doing is we're actually working in the quotient group, Z modded out by its subgroup NZ. And so the elements that we're working in there are really coming from these coset representatives. Okay, so our next theorem, if you let G be a group, if G is non-abelian, then if you take G and mod out by its center, so remember we saw before that the center is always a normal subgroup, so G mod Z of G is always going to be a quotient group, but this quotient group can't be cyclic if G is non-abelian. So the statement here, it's kind of interesting to phrase it this way. If G is abelian, then the center of it is the entire group. And so that means that G modded out by its center would be trivial. It would just, the center is all of it. And so G modded out by itself would just give you the trivial quotient group. That means that all you have is G. And so what this is saying is that in any case that G is non-abelian, then G modded out by its center cannot be cyclic. Okay, so we're going to prove this by the contrapositive. So by contrapositive. So let's use our new notation. So let's suppose that G mod the center of G is generated by G bar, and remember this is really talking about G times the center of G. Then let's let A and B be two elements of G. And so then this means that A bar has to equal G to the K, G bar to the K for some K. And B bar has to equal G bar to the L for some L. And so this really means that A is equal to G to the K, let's call it Z1, for some Z1 in the center. And B is equal to GL times Z2 for some Z2 in the center. Okay, and so let's clear out a little bit of space. Okay, so we have A is equal to G to the K times Z1, and B is equal to G to the L times Z2, where Z1 and Z2, these are both inside the center. And so then if we look at A times B, this is going to equal GK times Z1 times GL times Z2. But Z1 is in the center, and so if it's in the center, then and it commutes with any element, including GL, so I can move Z1 over. And so this is going to be equal to GK, GL, Z1, Z2. And then GK and GL, well, that's really just G to the K plus L, so it's just G times itself a bunch of times, and so I can reorder that as GL times GK times Z1, Z2. And then now I can use the fact that Z2 is in the center, and so it commutes with everything, so I can move it to the other side of Z1 and to the other side of G to the K. And so this is equal to G to the L, Z2, G to the K, Z1, which is B times A. And so for any A and B in the group, using the fact that we know where they are in these cosets coming from the center, we're able to rearrange this when we deform it into powers of G in the center to get it as being B times A. And so this tells us that G is abelian. Okay, so if G mod the center was cyclic, then G would have had to be abelian. That also means that if it was abelian, that the center was trivial to begin with. And so really all there was a single coset. And so these G to the K and G to the L, these were really just the identity. But that's what this proof implies. Okay, but this is an important fact to know, that if you know what a group is, and you know what its center is, then when you think about G modded out by its center, whatever group you have at the end, it can't be isomorphic to a cyclic group. It has to be isomorphic to something that's not cyclic if the G you started off with at the beginning is not abelian. Next theorem, so this is a theorem by Cauchy. So Cauchy, if you haven't seen Cauchy's name very much, if you keep taking math, you will start seeing it quite a lot more, because Cauchy is very important both in algebra and analysis and complex analysis. He pops up all over the place. And so this is a theorem of Cauchy's, and it says, let G be a finite group and let P be a prime that divides the order of G, then G has an element of order P. We actually will not be proving this full statement. We are going to be limiting ourselves to finite abelian groups. And so really I should put the abelian after the finite. And so the statement we're going to be proving is let G be a finite abelian group. To the broader statement that it's true for any group. This is a much more difficult theorem to prove, and it's a little bit beyond what we can do right now, but we can do it for the case in which we're dealing with abelian groups. Okay, so let G be a finite abelian group, and let P be a prime that divides the order of G. Then G has an element of order P. And so we're going to prove this by strong induction. On groups that are on groups whose order are multiples of P. So the base case is if G has order P, and as we've seen before, if G has order P, then G is cyclic and of order P. So its generator has order P, and then we're done. Okay, now for the induction step. So let's suppose that for any m less than n with p dividing m and p dividing n, we have that if G has the order m, then G contains a element of order P. Okay, now let's let G prime be a group with the order of G prime equaling n. Okay, and so using the what we have already proven, that we know that G prime has some element of prime order, and so this means there exists some G in G prime, not the order of G prime, just G prime by itself, with the order of G equaling Q, which is prime. Okay, so if Q equals P, we are done. So on the other hand, let's assume that Q is not equal to P. Okay, now let's clear ourselves some more space. So we're assuming that we have some element G and G prime, and the order of that is prime itself, but its prime order is not equal to P. So now we'll clear out some space. So now we will use that G prime as an abelian group really to help us out. So since G prime is abelian, well, in abelian groups, every subset is normal. And so then G prime, we can look at G prime mod G because the group generated by G, this is a group of order Q, is normal in G prime. And so then if we look at G prime mod the group generated by G, well, then this has order the index. So the order of this is G prime, the index in this, which by Lagrange's theorem equals n the order of G prime divided by Q, the order of the group divided by G. And so this is, since Q is prime, this is a order that is less than n, but it's still a multiple of P because Q is not dividing out P because Q is different than P. And so now we can use, by our induction hypothesis, we now have a group whose order is a multiple of P, but is smaller than n. G prime mod G has an element of order P. Let's call it X prime. And so then X prime to the P is the identity. And so this is equal to the identity in G prime over G. And so what that means is that X to the P mod G is equal to the subgroup generated by G, which means that X to the P is an element somewhere inside of G. Okay, so if X to the P is inside of G, so if X to the P equals the identity, then we're done. We found an element of order P. Otherwise, since the G has prime order, that means that the order of X to the P is equal to Q. Now let's clear out some space again to give us some room to work. So if X to the P has order Q, then my claim is that X has order PQ, because it can't have order P is not equal to P, because we already said that X to the P is not the identity. And if X has order Q, that would mean that X bar to the Q is equal to E bar, but we already know that X bar has order P, so we already know that X to the P is equal to E bar, and so then we'd have that X to the R is equal to the identity in the quotient group, where R is congruent to Q mod P, and since P and Q are different primes, R can't be 0, and we can choose R. So R can't be 0, and we can choose it to be less than P. And this would contradict that P was the order of X bar. And so we get a contradiction there. And so then the only possibility is if the order of X is P times Q, the order of X has to divide P times Q, but it can't be P, it can't be Q, and it can't be the identity for the same reasons as we saw before. And so it has to equal PQ. And so that establishes the claim. And then that means that the order of X to the Q equals P. So X to the Q, and this is in G prime, is an element of order P. Okay, one last bit to talk about at the end. And so we have a group, we're going to say that it is an internal direct product of H and Q if H of H and K, if H and K are normal subgroups with their intersection being the identity, and if for any element G and G, there exists some H and N such that we can write G is equal to HN, right? And so really, this is really saying that if you take the product of H times the product of N, you get G back, okay? And so what's the importance of this? Well, if you know that G is an internal direct product of two normal subgroups H and K, then that means that H is going to be isomorphic to G modded by K, so the quotient group G mod K. And so just a quick map here, the isomorphism is very straightforward. The isomorphism from H to G mod K is going to send H to just the coset HK. Okay, and so my claim is that this is one-to-one and onto. Let's do onto first. So this is for any G sub K in G mod K. Well, G we can write as H times N. So G is equal to HN for some, I really should have put, that should be a K there. Sorry about that. So G is equal to HN, where H is in H and N is in K. And so then that means that the left coset GK is equal to the left coset HK. So for this H, phi of H is equal to GK. And so again, this is using that cosets are equivalence classes. And so this gets us what we want. Showing one-to-oneness is also very straightforward. So if phi of H1 is equal to phi of H2, then that would mean that H1K is equal to H2K, and so that would mean that H1 is equal to H2 times N for some N in N. But then that would mean that H1, that H2 inverse H1 was equal to N. And so since H1 and H2 are both in H, and N is in K, getting confused between my K's and N's again. Since H2, H1 are both in H, so H2 inverse is in H, and N is in K, this means that H2 inverse H1 is in both H and K, so it's in the intersection, and so that means that H2 inverse H1 is the identity, and so H1 is equal to H2. Okay, and so that gives us one-to-oneness. Now, last but not least, we need to show that it plays around with the group operations, but that is, we've already seen that. That's what the definition of the quotient group is. And so that the fact that this is going to play around with the group operation on both sides, this is already given by the fact that we're working in the quotient group. And so this map is So it is 1-to-1 and onto, so it's a bijection, and then we get that it plays around with the group operation automatically. And so that finishes this theorem. And that is all for this video. I know it's been a long one. Thank you for sticking it through, and I will see you again soon.